So last time we began talking about Archimedes. So let me just give you a couple of quick highlights from that. And then today, what I'm going to do is give you an overview of some of the work that Archimedes did. And some of these topics we'll explore more later. So he did many things, including math, physics, and even inventions. We know that he died in the year 212 BCE because that was the day that the city where he lived, Syracuse, was captured by the Romans. We looked at the story of Eureka, where he discovered a method of figuring out whether a crown was made out of pure gold or whether it was he was being cheated by the goldsmith. One example of his laws is the law of buoyancy, which says that an object loses weight, in other words, experiences an upward force equal to the weight of the water that's displaced by the object. And then this was the war that I was referring to. It was Rome versus Carthage. The Roman general actually wanted Archimedes to be captured alive because Archimedes was a great inventor. And so the general of the Romans was hoping that Archimedes would be captured and would help them in the war effort. But the story goes that when a soldier came to arrest him, Archimedes was busy drawing geometric figures in the sand. He didn't want to come right away, which caused the soldier to kill him. And Archimedes, the quote was, "Don't disturb my circles." Okay, so that's what we did last time. Now today, I want to talk about a few of his famous works. So the first one is a theorem. And the theorem is that the ratio of the volume of a sphere to the volume of the enclosing cylinder. So in other words, so you take a sphere and you basically draw the smallest cylinder you can that completely encloses the sphere. So basically, the sides of the cylinder touch the equator of the sphere, and then the top and bottom of the cylinder just touch the North Pole and South Pole of the sphere. So basically, it's the smallest cylinder that can completely enclose the sphere. And then the theorem is that the ratio of the volumes is 2 to 3. Now, the proof uses the method of exhaustion, which is a method that he used for quite a few of his results. So here's a question. Can we derive the modern formula for the volume of a sphere from this theorem? So we're using the fact that, number one, We know what the area of a circle is. It's pi r squared, where r is the radius. And then we also know how to calculate the volume of a cylinder, and that's just the area of the base times the height. So we know all of those numbers. And so what is the formula for the volume of a cylinder? It's the area of the base, which is pi r squared, times the height. And the height of the enclosing cylinder is twice the radius. And so we're going to get 2 pi r cubed. And that's just for this particular cylinder. So for this particular cylinder, the volume is 2 pi r cubed. But according to Archimedes, the ratio of the volume of the sphere to the volume of the cylinder is the same as 2 to 3. So as modern people, we write the ratios as fractions. And so therefore, the volume of the sphere is 2/3 the volume of the cylinder. So let's go ahead and do that. So that's going to be 2/3. And then the volume of the cylinder is going to be 2 pi r cubed. And then when we simplify that, we get 4/3 pi r cubed. And so basically the modern formula for the volume of a sphere is just a simple consequence of Archimedes' theorem. And so this is the first example of a good formula for actually calculating the actual volume of a sphere. But interestingly, there's more. So the ratio of the surface area of the sphere to the surface area of the enclosing cylinder is also 2 to 3. So it's the same ratio. How did he prove this? Well, he used the method of exhaustion. So let's see if we can do the same thing. Can we derive the modern formula for the area of the surface area of the sphere from this theorem? And the answer is, again, yes, we can. So let's assume that we know the following things. We know a circle has area pi r squared. And then the other piece of information that we need to know is that the circumference of a circle is pi times the diameter, but remember that the diameter is just 2 times the radius. So in other words, it's 2 pi r. This is, in modern terms, the more common formula for the circumference of the circle is that the circumference is 2 pi r. But both formulas are equivalent. So now when we're calculating the surface area of the cylinder, there's 2 things we have to consider. So basically, the cylinder has 3 separate parts that go together to form the cylinder. So you've got the top of the cylinder, you have the bottom of the cylinder, and then you have the sides. So the side that goes all the way around. So in calculating the total surface area of the cylinder, let's begin by the top and bottom. Well, those are just circles, and so they have area pi r squared. Now, how do we calculate the area of the side that goes all the way around the cylinder? Well, the idea is, so imagine you just cut it and then you unroll it and flatten it out. And when you do that, you get a rectangle. So here we go. Let's unroll the side of the cylinder. It becomes a rectangle. And then we know how to calculate the area of a rectangle. It's just going to be the width times the height. And so let's go ahead and do that. The width is 2 pi r. And then the height of the cylinder, as we saw before, is 2 times r. And so when we simplify that, we get 4 pi r squared. So let's just call this the hollow cylinder. It's the cylinder without the top and the bottom on it. And so what's the total area? It's going to be the area of the side, which we said was 4 pi r squared. The area of the top was pi r squared. The area of the bottom was pi r squared. And so we get that the total area is going to be 6 pi r squared. And so the ratio of the area of the sphere to the area of the cylinder is 2 to 3. So writing the proportion again as fractions, that means that the area of the sphere is 2/3 the area of the cylinder. So let's go ahead and plug in the formula that we got for the surface area of the cylinder. So we get 2/3 times 6 pi r squared. And so we see that we have a factor of 3 in the denominator and a factor of 3 in the numerator. Let's get rid of that. And so we're going to get 2 times 2, which is 4 pi r squared. So that's going to give us the surface area of the sphere. Now here's an interesting thing to observe. So what was the area of the hollow cylinder? That was 4 pi r squared. What's the area of the sphere? It's 4 pi r squared. It's exactly the same. And so as a result, we get yet another theorem, and that is that the surface area of the sphere is equal to the surface area of the enclosing hollow cylinder. So the cylinder that is missing the top and the bottom. And Archimedes knew this theorem as well. Now, just a little aside. So for modern people, there's a fun heuristic. So in mathematics, we use the word heuristic to mean an informal argument that isn't a proof, but it supports an idea that something is true. Remember that when Archimedes figured out how to find out if the crown was pure gold or not, he ran through the streets shouting "Eureka," which means "I have found it." And so the Greek word heurisko means to find or discover. And so our modern word heuristic basically means an informal discovery coming from that same Greek word that that Archimedes used when he discovered his idea for figuring out if the crown was fake or not. Okay, so let's say that we know the volume of a sphere. If you differentiate that formula with respect to r, you get 4 pi r squared, which is the surface area. Let's see if that works in 2 dimensions. Let's say that we know the area of a circle. Let's differentiate that with respect to r, and we get 2 pi r, which is the circumference of the circle. So just kind of a fun little heuristic there. Okay, so now let's look at the tomb of Archimedes. So here's something written by Plutarch, who was an ancient author. And here's what he said. So he's writing about Archimedes. And here are some things he said. So he forgot food and neglected his person, so meaning neglected to care for himself, to the degree that he was occasionally carried by absolute violence to bathe or have his body anointed. So he literally was not taking care of himself, apparently. And being in a state of entire preoccupation with his discoveries. So with his love and delight in science in general. So his math, his physics, his inventions, all of that. So his discoveries were numerous and admirable, but he said to have requested to his friends and relations that when he was dead, that they would place over his tomb a sphere containing a cylinder, inscribing it with the ratio which the containing solid bears to the contained. So in other words, what did Archimedes want inscribed on his tombstone? This illustration of the sphere inside of the enclosing cylinder, along with the corresponding ratio from his theorem. So that's what Plutarch writes. So did it happen? Well, a famous Roman, Cicero, wrote the following 137 years later, so in 75 BCE. And so basically what he writes is that he wanted to look for the tomb of Archimedes. And so he says, I managed to track down his grave. Finally, let's just look at another little bit of this. Finally, I noted a little column just visible above the scrub. It was surmounted by a sphere and a cylinder. So apparently, this actually happened, and Cicero found the tomb. And then here's just a painting that's an illustration of this story of Cicero discovering the tomb of Archimedes. Okay, so now we're going to take a look at yet another idea that Archimedes had. So here's a famous quote by Archimedes. So I won't read the Greek, but let me just point out a couple of the words. So basically what this says is, give me a place to stand, and with a lever, so that's this, I will move, that's this word right here, the whole world. So whole is here, and that's world. So this is what Archimedes said. And so basically what he did was he developed some principles of the mechanics of levers. This illustration here is of Archimedes moving the world with a lever. So here's Archimedes' law of the lever. So here's the scenario. So what you have is a lever. So it could be like a plank or something that's balancing on a fulcrum. You have a weight on this side and a weight on this side, and each of these weights are at a fixed distance from the fulcrum. So we're using the letters capital W and capital D on one side, lowercase w and lowercase d on the other side. And so the law of the lever says that the product of the weight and distance on one side is equal to the product of the weight and distance on the other side. So that's what this says. So the bottom line is that even if this weight is really big and this weight is really small, you can still make the lever balance as long as this distance is big enough. So in other words, what distance do we need? The first weight times distance divided by the second weight. Now, as an illustration of this principle, if you ever as a kid used a seesaw at a playground, and maybe you had an older or younger sibling and your weights were very different, you probably discovered yourself that if the heavier person moves forward and the lighter person moves back, then you can go ahead and use that. So that's just an illustration of this principle. So let's just look at an example of this. So in this example, the first weight is 4 ounces, and the first distance is 2 centimeters. The second distance is 3 centimeters. What weight over here is going to make this balance? So this is what we're calling W. So what we're going to do is we're going to take the weight times distance on the left-hand side, that's 4 times 2, is equal to the weight times distance on the right-hand side, so that's W times 3. And so now we just need to solve for W by dividing both sides by 3. So we're going to get the weight is 4 times 2 divided by 3, which is 8/3 of an ounce. So that's the law of the lever in action. Now, the next idea has to do with, so how do we find, for example, the exact area of a circle? So the first idea is cutting a circle and then rearranging it. So we're going to see that what Archimedes did was he took the circle and he basically made a cut, and then he opened it up to form a triangle. And so the width of the triangle is just the circumference of the circle, because remember, he's opening it up. And then what's the height? It's going to be R. So if this picture is accurate, then the area of the circle should be equal to the area of this corresponding triangle. And so what's the area of the triangle? It's going to be, it's always 1/2 times the base times the height. So let's plug in the actual numbers. So 1/2 times the circumference times the radius. So that should be the area of the circle. So this leads us to the modern formula for the area if we first define pi to be the ratio of the circumference to the diameter. And so this would give us that C is equal to pi times D. D is 2 times R. So that gives us the formula that the circumference is 2 pi R. So then using this, what should the area of the circle be? The area should be the area of the triangle, which is 1/2 times the circumference times the radius. So let's plug in those numbers. There's your 1/2, there's your circumference, 2 pi R, there's your radius. And so we see that the 1/2 and 2 cancel out. And so we're going to get pi R squared for our formula. So the trick is, how do you actually prove this? So Archimedes was the first to prove that the area of the circle with radius r has the same area as a triangle with width c and height r. So this is equivalent to the modern formula A equals pi r squared that we just saw. So this picture here is an illustration of an informal proof that the circle has the same area as the triangle, whose base has length c and whose height is r. And let me, before I go on to his idea, let me just elaborate on this a little bit. All right, so let's start with a circle. And then what we're going to do is imagine that we are approximating the circle with a polygon. And so what I'm going to do is all right, so this is going to be a very crude drawing. Oops. So in this picture, the circumference of the circle is almost exactly the same as the perimeter of that very crudely drawn blue polygon. When you straighten that out, here's what it looks like. So basically, each of these triangles is going to now be like that. So you've got a bunch of triangles. After you straighten that whole figure out. But that's a bunch of triangles. That's not just one triangle. How do I take that and make one triangle out of it? Well, here's an observation. So let's just look at one of those triangles. So let's say this is the base, and that's the height of the triangle. Well, it turns out if you draw another triangle that's maybe tilted from the first one, but it still has the same base and the same height, it's going to have the same area. And so here's what you're doing basically. So this first triangle is being replaced with that one. The second triangle is being replaced with that one. Oops. The third one is being replaced by that one. The fourth one is being replaced by that one. So basically, this triangle right here has the same base and height as this one. So basically, I'm just smooshing all of the triangles together without changing the area. And so this gives me motivation to believe that that the results are correct. Okay, so that's our rough idea. Now let's take a look at what he actually did. He used the method of exhaustion. So what he did was, so just like in this illustration here, where I drew a polygon that's very close to my original circle, that has a perimeter that's almost the same as the circle, and it has an area almost the same as the circle. Well, he basically used that idea, but he made it precise. So he used both inscribed, so those are polygons drawn inside the circle, and circumscribed, those are the polygons drawn outside of the circle. So here's the illustration. So here's the circle. The green is an inscribed hexagon. So you can see that the hexagon just touches the circle at each of its corners. And then we have a circumscribed hexagon where each side, like right in the middle of the side, just touches the circle, is actually tangent to the circle. So it touches the circle in exactly one point. So that's what the inscribed and circumscribed hexagons look like. But he didn't just use hexagons. So he used these polygons to estimate the area, and he repeatedly doubled the number of sides, starting with hexagons. And then basically, you're going to get areas of the inscribed polygons. So those are going to be P1, which is the hexagon, P2 would be the dodecagon, etc. And in every case, because the polygon is completely enclosed within the circle, its area is going to be less than the area of the circle. We repeat the process for the circumscribed polygons. So we're going to call those areas Q1, Q2, Q3. And since these polygons completely enclose the circle, the area of the circle is going to be less than those. So those areas are bigger than the area of the circle. And then what we want to do is, in modern terms, we would say we would take a limit. But what he did was he basically observed that you can, by taking enough sides, you can make the area of the outer polygon minus the area of the corresponding inner polygon less than any arbitrarily small amount. Now, he also used this trick to estimate pi. And here's what he came up with, that pi is going to be greater than 3 and 10 over 71, and it's less than 3 and 1/7. Now, of course, he didn't use the modern symbol for pi notation. Basically, he's estimating the ratio of the circumference to the diameter. So when I say pi here, he was really saying the ratio of the circumference to the diameter. So for example, when you do n equals 6, and so that's these inscribed and circumscribed hexagons, this is what you get. And so after you do this, then you take all the information you learned from that step, and then you double the number of sides, and then you use math, including, of course, the Pythagorean theorem, to figure out all the missing numbers, and then you calculate those areas, and then that's going to give you a new estimate. Now, in Archimedes' case, he stopped when he got to a 96 gon. So that was his last step. But of course, the way that he did it, his method allowed him to keep going forever. But in any case, the estimate that he got was this, using the 96 gons. So basically, this is going to give you, for example, with the 3.14. So here's just an illustration of how this process would look for hexagons. So for the inscribed hexagon, basically what you're going to get is these are all going to be equilateral triangles. So if the radius is r, then this is also r. And so therefore the perimeter is going to be 6r. The diameter is 2r. So you get 6r divided by 2r. And that's how you get the 3. The circumscribed case is a little bit harder, but it's not that hard. So basically what you have to do is figure out what the length of the side is. And basically all you have to do is, you know that this is r, this would be half of x, this is x, because these are equilateral triangles. And you can just use the Pythagorean theorem, and then you calculate the perimeter divided by the diameter, and then you get 3 times the square root of 2, or rather 2 times the square root of 3. That was a typo. Let me fix that. And after you do that, what you would do next is, for example, this one, you divide that in half. You do that with all of the triangles. Now you have some new pieces of information you need to figure out in order to calculate the new perimeter. And then you do the same thing for the circumscribed. Okay, so now what I'd like to talk about is the Archimedes palimpsest. So typically parchment, which is made out of animal skin, was used for writing, but it was also very expensive by virtue of it being scarce. And so what they did was they often, when they were done with something, they would scrape it, wash it, and reuse it. So they would write over it. So I'm done with this writing, so I'm going to scrape it and then use it for something else. But after some time, the washed out writing starts to show through again, because this was an imperfect process of cleaning the parchment. And it turns out that in modern times, we can often read what's underneath by using UV light or X-ray fluorescence imaging. So using modern imaging, not modern non-destructive imaging techniques, we can often read what the underlying writing is, even though it's been erased. Now, this image is of the Archimedes palimpsest, which is currently in the Walters Art Museum in Baltimore. So let's look a little bit at the history of this sample of writing and then what's on it. Okay. So in Jerusalem, in 1229 AD, the greatest works of the Greek mathematician Archimedes were erased because whoever owned these particular copies didn't need them anymore. And so they erased them and overwrite them with a prayer book by a priest. We even know his name. And then let's see what happened after that. Well, in the year 1899, somebody noticed this particular works in a Greek Orthodox church in Istanbul. And basically what they could see was that there was some math that was kind of showing through in this prayer book. And so what they did was they photographed it, and then they began translating at least as much of it that they were able to read. They weren't able to read the whole thing, but they were able to read some of it. And so they worked on translating what was there. However, during a turbulent time, it was lost in the 1920s. Allegedly, it was bought from a monk. Now, by the way, nobody believes that. It was stolen. So the person who owned it, or rather his descendants, claimed that, oh yeah, it was bought by a monk. It was fine. So it was bought by a businessman who basically hid it. So he knew that he wasn't supposed to have it. So he didn't display it. He didn't tell people he had it. But after his death, his daughter sold it at auction at Christie's. Now, by the way, so when it did turn up at the auction, the Greek Orthodox Church had a lawsuit against them saying this thing was stolen from us and we want it back. The problem is that it was so many years later that they really couldn't prove it either way. And so the court decided in favor of the daughter, or rather Christie's auction house. And so they allowed the sale to go through. Now, who bought it? Well, an anonymous American high-tech buyer, and the representative of the buyer said, it's not Bill Gates. So we actually don't know who it was. In any case, the buyer paid $2 million for it. And then the buyer, whoever it is, allowed this to be displayed at the Walters Museum and allowed high-tech imaging in order to extract more text. So the bottom line is that they were able to get a lot of this text from this document. So what was on it? Well, it's a work called The Method. And so basically, it talks about the proof by exhaustion. So if you think about it, the first comment is, so it's great that you can do a proof by exhaustion of these, various facts, but how did you figure that out in the first place? Why would you have thought to do what you did? So in other words, what were the heuristics? So remember, the heuristics are informal reasoning that makes you believe that something is true without it being a proof, like that example that I gave of the dissecting a circle into triangles and smushing them together. So that's an example of heuristics. So basically, in the method, Archimedes explains his reasoning. So what did he do? He did things like slicing up objects. And surprisingly, in places where you would least expect it, he even uses the law of the lever. And some of these results are, and kind of the thought process behind it, is actually very close in spirit to calculus. Okay. So now what I would like to do is just give some highlights of some additional items. So this illustration here is the screw of Archimedes. So what does it do? It's an ingenious device for basically, so you have water down here, and then you rotate this, and it causes the water to come up to a higher place. So it's a contraption for bringing water from a low place to a high place. So kind of cool. He had a model of the planets. We're going to talk more later about his methods for trisecting angles. Another really amusing thing, this is an example of an invention. He developed a pulley system which was capable of moving ships around on a dry dock. So that's pretty cool. He also had 13 Archimedean solids. So these are not Platonic solids. So the Platonic solids, remember, are comprised of, you have a certain number of identical regular polygons. So for example, the icosahedron has 20 equilateral triangles, but these solids, like for example, something that's like a soccer ball, contains a mix of hexagons and pentagons, but then it's formed into a solid. And there are 13 of those. So here's something that we're going to look at later, and that is the spiral of Archimedes. So Archimedes is trying to solve some of the three famous problems of antiquity. So we're going to continue seeing examples of people trying to solve these problems. So he uses the spiral to trisect angles, but also he uses the spiral to square a circle. And so we're going to see more on this later. Here's another interesting thing that he did. And this is quadrature of a parabolic section. So remember that as long as you can take a curved figure and then you can convert it into any polygon, we know how to square any polygon at all. And so any process that converts a rounded figure into a polygon is basically, you have all the information you need for squaring that rounded figure. So a parabolic section, well, a typical parabola would be something like y equals x squared, or y is equal to a constant times x squared. And then what we're going to do is we're going to draw a line. It doesn't have to be parallel to the x-axis. You just draw any line at all. It's going to cut off a section of the parabola. So it's round, so you get an area that's bounded by the parabola in a line. And then what did he prove? The ratio of the area of the parabolic section to the inscribed triangle is 4:3. So that's all you need to be able to square this parabolic section. Okay, so that's all I have for today as far as new content. Let me just remind you, though, that we have an exam that's coming up in a week and a half. The study guide will be ready within the next day or two at most. Probably a preliminary study guide will be going up very soon. It's going to cover the material up until next Tuesday's class. So it's going to include at least some of the material on Archimedes. It's going to follow the same format as the last exam. So you're going to have a combination of short answer questions. So it might be who did quadrature of a parabolic section, and you would say Archimedes. That would be an example of a 2-point question. It will have some 5-point questions. So those are going to be the simpler, like math questions. And then finally, you're going to have a few longer questions, just like we had last time. And so the longer questions, so constructions will be on the exam. Make sure that you bring your compass and straight edge. An example of a 5-point construction might be, construct parallel lines. An example of a 10-point construction question might be construct a pentagon, like you're doing on the homework that's due later today. Okay, so any questions about that or anything that we covered today before we break up? Okay, so there's a question about the homework due date. And let me double check. I'll have to make sure that the date is correct on the grade scope. So if it's incorrect, I'll go ahead and fix that. Okay, so any other questions? So I'll be hanging around for a few minutes after class. If anybody has any questions they'd like to ask, if you're struggling with something on the homework or whatever. And otherwise, have a great weekend, everybody. And I will see you in person on Tuesday. Bye, everybody.